Right, continuing section 12.4. So we left last time after learning about the definition of the principal unit normal vector. So now we're going to refresh our memory by doing another example that involves that. And then talk about some applications. So first off, if I want to find the principal unit normal vector, remember that has a very specific meaning. Right, it means I want to find t prime of t divided by its magnitude. Little arrow. Yeah. All right, so to start with, we would need to figure out the derivative of our vector valued function. Okay, so starting off with 2 cosine t, we'll have the derivative negative 2 sine t. That's our I component. 2 sine of t will have derivative 2 cosine of t. That's the j component. And then t will have a derivative of 1. So we'll write plus k. So this is our derivative, r prime of t. Remember, if I want to get t prime of t, or not even t prime of t, if I want to get t of t, right? Remember that is equivalent to this derivative vector that we just found divided by its magnitude. So off to the side, we'll figure out the magnitude of r prime. Keep in mind, this doesn't specify a value of t to plug in, so we have to just use the components as they are. So I have the square root. If I square my I component, I get positive 4 sine squared of t. If I square my j component, I get plus 4 cosine squared t. And then if I square my k component, I get 1. So one thing we should recognize is that these first two terms almost look like that trig identity that has come up a couple of times. If I were to just factor a 4 out from those first two terms only, this is what we would get. All right. And well, we know that this part here is equivalent to 1. So altogether, under the square root, we have 4 times 1 plus 1, which will give us the square root of 5 as the magnitude. Notice that's not actually even dependent on t. It doesn't matter what t is equal to, the magnitude of r prime will always be square root of 5, which is nice and convenient. So our unit tangent vector, t of t, is going to be 1 over the square root of 5. Remember, we divide by magnitude times negative 2 sine of t I plus 2 cosine of t j plus k. So now, to get my principal unit normal vector, I need to take the derivative of the unit tangent vector. So t prime of t. Remember, when taking derivatives, if you have a multiplicative factor, it can stay out front. Okay, derivative of negative 2 sine t, we get negative 2 cosine t. Derivative of 2 cosine t, we get negative 2 sine of t. And then the derivative of 1 is 0, so we no longer have a k component. And now that we've determined t prime of t, we're going to need to find its magnitude in order to get our principal unit normal vector. So the magnitude, all right? To compute the magnitude, we could distribute this 1 over square root 5 to both of these terms, right? So when I do that, this becomes negative 2 over square root 5. Now think about what would I get if I squared that? I'd get positive 4 over 5. Now, similar thing here. If I distribute, I get negative 2 over square root 5. So if I square that, I get positive 4 over 5. So then, shorten my root here a little bit. All right, so then when I combine these, I have the square root of 8 over 5. All right, so let's keep in mind that this is equivalent to 2 square root 2 over the square root of 5. All right, because 8, remember, is 4 times 2. Square root of 4 is how that 2 got there. And if you take the square root of a fraction, it's the square root of the top over the square root of the bottom. Oh, you know what? Oh, yeah. Okay, that explains that. Yeah, I made a silly. I forgot about our friends sine and cosine. Yeah, no need to erase all of it. Just keep it there for a sec. Okay, so remember that we will still have cosine squared t and sine squared t. Thing about that is I can factor the 4/5 out just like we factored the 4 out up here, right? So when I do that, we're going to end up with 4/5. So this whole thing is equivalent to 4/5 times sine squared t plus cosine squared t. Doesn't matter what order I add these in. So yeah. Um, and remember that's 1. So this is really just the square root of 4/5, not 8/5. Yep. So instead of getting 2 square root 2 over 5, we're just going to get 2 over the square root of 5. All right, square root of 4 is 2 divided by square root of 5 gives us that norm. Okay, so then my principal unit normal vector, n of t, is defined as the derivative of my unit tangent vector divided by its magnitude. Okay. So keep in mind, if I have to divide by 2 over square root 5, that's the same thing as multiplying by its reciprocal. So we already have 1 over square root 5 from earlier. If I multiply by the square root of 5 over 2, um, I end up getting just 1/2, right? Then we still have our minus 2 cosine t I minus 2 sine t j. Microscopic writing. Yep. All right, so then when I distribute that 1/2, we end up getting our final answer, negative cosine of t I minus sine of t j. And that is our principal unit normal vector for any value of t that we decide to plug in. And there we go. So kind of summarizing that process, okay? If I want to find a unit tangent vector, all I need to do is take r prime and divide it by its magnitude, whether I plug a value in for t or not. Furthermore, if I want to find the principal unit normal vector, I have to do all that. So get my unit tangent vector. take its derivative and divide by the magnitude of that derivative. And again, I might have to plug a value in for t, I might not. Right, and watch out for trig identities and things that can make your life easier when you simplify. Pro tips. All right. So, one other thing that tangent vectors and normal vectors are useful for is it allows us to actually decompose acceleration vectors into tangent components and normal components. Well, tangential components and normal components, which can definitely be helpful to us because remember what I said earlier. Acceleration is something that we tend to fixate on because it's used in the calculation of a force. Force is mass times acceleration. If I can decompose my acceleration into tangential components and normal components, then that allows me to find magnitudes or even values for different forces that combine to make a force. So the example that I talk about in this little snippet here is like if you have a styrofoam cup, let's say that you attach a string to that styrofoam cup and fill it part of the way with water, right? If you were to spin the cup around from the string, you would notice that the water actually stays in the cup, which means that there has to be a force holding the water into the cup. You also notice that if you were to let go of the string at any time, the cup would go flying off in a particular direction. Specifically, it would become a projectile where your tangent vector, right, is the initial velocity vector, or the tangential acceleration is the initial acceleration, right? Um, but going back to what's keeping the water in, that happens because as we spin the cup around, right, in that circular motion, there is a force that's acting in the direction of the bottom of the cup, right? In particular, it's always perpendicular or orthogonal to the tangential vector that we just talked about. So in physics, you would learn that that's called centripetal force. And here, being able to decompose our acceleration like we're about to allows us to quantify the centripetal force. If you've ever ridden on one of those rides that's like a tilt-a-whirl and goes around and around and it pins you up against the wall, that's centripetal force also. Yeah, bad memories. Anyway, so to understand how the formulas work, because there's a lot of different ways, as you can see on the note sheet, there's a lot of different ways that you can compute these different components. Right. And it all kind of boils down to remembering what we learned about projection back in chapter 11. Right. So the tangent vector and the normal vector. So if I have an object that's moving along some kind of a path, right, the tangent vector would be represented like this. The normal vector would be represented by like this, right? So you have the force that's moving the cup in that circular path. You have the normal force that is keeping the water in the cup, i.e. your centripetal force, like that. So these two vectors, and really any two vectors form a plane, but these two vectors in particular form a plane where we are always guaranteed to have our acceleration vector. So the acceleration vector is always somewhere in this plane. So this is our tangent, this is our normal. The acceleration vector is always in the plane defined by these two vectors. And if you ever take linear algebra, you would learn that that actually has an implication, that the acceleration can always be written as a linear combination of these two vectors. In fact, that's exactly what we're saying here. The acceleration, right, is always equal to a combination of the tangent vector and the normal vector. Okay. So AT is what we call the tangential component of the acceleration, and A sub n is what we call the normal component of the acceleration. And if you look at if you look at these vectors here, you can see that we're to draw this kind of like an XY plane, right? The projection onto the normal vector, right? So projection onto the normal vector of the acceleration vector will result in this term here. Likewise, the projection of the acceleration vector onto the tangent vector will result in this term here. So when we're asked to find things like the tangential component and the normal component, we're just being asked for these values, a sub t, a sub n. So these are some different formulas that we can use to calculate our tangential and our normal components for acceleration. There's not one always correct. There's not one, this is always the one that you should use because it's easy. It all depends on what information you have available to you. If it's easy for you to get your unit tangent vector and you already know what your acceleration vector is, or you can also easily find it, then this dot product formula is pretty easy. If it's easy for you to figure out the principal unit normal vector, which we've seen can get very hairy sometimes, right? Then you could use that to find your normal component of your acceleration. But you also have all of these options available to you. Like I'm going to tell you right now, this is probably way easier to do than this most of the time, right? Or even this. Because I mean, if you're calculating the magnitude of t prime, you may as well get the normal vector, right? Or if you already have to figure out the tangential part of the acceleration, this might be an easier one to do. So let's look at an example and kind of see how these might apply. By the way, I'm going to say don't worry about memorizing these. I'm going to be nice and actually have this on your exam for you to see the formulas, right? So looking at this example, find the tangential and normal components of acceleration for the position vector given by this. So this gives us the pathway. We want to find both components of our acceleration. So let's start off by getting the first derivative of r. So if I take the first derivative of r, we can go component-wise. That's going to give me 3i minus j plus 2tk. Now, now that I have that, I'm going to label this as my velocity vector, v of t. And we've arrived at our first option. If I want to find the tangential component of the acceleration, I could find the magnitude of my velocity and take its derivative. I mean, that would be a simple chain rule. It wouldn't be too hard to do. Um, Another option is that I could go on and get my unit tangent vector like we've already done here. Another option is I could get the acceleration vector, do this dot product, and then divide by the magnitude. I wouldn't do this one because, frankly, if I'm getting the magnitude of my velocity, I may as well do this. Similar thing, I would have to get the magnitude of the velocity anyway to get t. So if I were doing this and I were in a hurry, I would probably go with this one because if I were to take the magnitude of this, the worst case scenario is I have to do a chain rule. So let's take a look. If I find the magnitude of my velocity, we'll get the square root of 3 squared, that's 9. Negative 1 squared, that's 1. So 9 plus 1. And then 2t squared, remember both the 2 and the t are squared, so we get 4t squared. Altogether, that gives me the square root of 4t squared plus 10. Now, before I move on to finding the derivative of this, I want to remind you that when you have a bunch of stuff under a root, it's often helpful to write the root as a power, right? So that when I go to take the derivative with respect to t of this magnitude I just found, I know that I can just blah, blah. I know that I can just do chain rule. So I'm going to bring my 1/2 down. Remember, the inside doesn't change. I'm going to take 1 away from the power, so minus 1/2, multiplied by the derivative of the inside. So it'll be 8t. We know that this is equivalent to the tangential part of our acceleration. So we're going to write, whoops, it's not a vector. So we're going to write a sub t is equal to, and then multiply 1/2 times 8t. Remember, you cannot do anything with this. It's raised to a power, right? This is not, so I can multiply the 1/2. And I get 4t divided by the square root of 4t squared plus, whoa, writing and talking faux pas. 4t squared plus 10. Right, so this is going to be the tangential component of my acceleration. If I were given a value of t, I could plug that into this formula, but I want you to know if you are given a value of t, don't plug it in until after you've taken this derivative, right? Otherwise, you'd be differentiating a constant and you would say it's 0, and I'd be like, what? That's not right, you silly goose, right? So take the derivative first, plug the t in later, if you have a t to plug in. But anyway, we got our tangential component. Now to find our normal component, again, we have all these different ways that we could do that. I know I'm going to need my acceleration vector for this, no matter which method I use. So I'm going to find that first. So the acceleration vector as a function of t is going to be the second derivative of our position. So if I take the derivative of 3, that's 0. So there's no I component. If I take the derivative of -1, also 0, so there's no j component. And then if I take the derivative of 2t, I get 2. So our acceleration vector is 2k. Now that we have the acceleration vector, we can go with whichever of these is simplest. Again, since we already have our tangential component, I would go with this one. But we also have both the velocity and the acceleration vector. So if you really enjoy taking cross products like I do, you could do this one. But I'm going to go with this one. So I have the square root of the magnitude of the acceleration squared. So think about it, the magnitude of the acceleration is going to just be 2, right? Because 0 squared plus 0 squared plus 2 squared gives you 4. Square root of all that, you get 2, right? And whenever you get to where you only have one component, then that is going to be your magnitude. Right, think about it in space, it would just be going straight up the z-axis 2 units. So you already know the length is 2. So anyway, we know that the magnitude for acceleration is 2. We're going to square that. Subtract from that the tangential component of our acceleration, which is this guy. And we're going to square that as well. So if I were to simplify this, we get 4 minus 16t squared over 4t squared plus 10. And if you really wanted to go further, you could make a common denominator, subtract them, make it one fraction, and be a third grade math superstar, but I'm going to leave it like here. So this is the normal component of our acceleration. This was our tangential component. So again, you don't need to memorize these, right? But you should be able to look at them and say, given this information, this one will be the most, or really the least horrible to do. Okay, now with that said, let's do 2 more examples. Okay, so we want to find the tangential and normal components of the acceleration for a helix. All right, and here we don't know the value of b, we just know that it's a positive number. Right. So with that said, remember for all of these, we have to start off by figuring out our velocity vector, r prime. So derivative of b cosine of t will be negative b sine of t, I. All right, derivative of b sine of t is b cosine of t, j. And then derivative of ct is c, and that's k. So we've got our velocity vector. Remember our options. We can take the magnitude of the velocity and take its derivative. We can take the magnitude of the velocity and get the unit tangent vector. We can do all sorts of stuff. Either way, our next step should be to find the magnitude of the velocity vector. So we have the square root of, now we're going to square each of our components. So if I square my I component, I get positive b squared sine squared t. If I square my j component, I get b squared cosine squared t. And then if I square my k component, I get c squared. KL. We're going to have to use that trick again, that trig identity. Notice from these first 2 terms, you can factor out a b squared. You're going to leave behind sine squared t plus cosine squared t. And we know at this point emphatically that this is equal to 1. So these first 2 terms simplify to just b squared. So we get the square root of b squared plus c squared. And no, it's not a. No. All right, this is just, we don't know what b is, we don't know what c is, we just know that b is a positive number, which doesn't really matter because that's squared, but yeah. So this is the magnitude of our velocity. So if I go now and take the derivative of this with respect to t, I know that this is going to give me the tangential component of my acceleration. Here's the thing though, b is a constant. c is a constant, which means that the derivative of all that is 0, which means that there is no tangential acceleration when you're moving along a helix, which is an interesting little property. Okay, now that we have our tangential component for the acceleration, we can get the normal component. Remember, with the normal component, our first step is to find the acceleration vector, which is going to be the second derivative of r, the position. So derivative for negative b sine t will be negative b cosine t. That's the I component. Derivative of our j component, we get negative b sine of t. And then derivative of c, a constant, is 0. So we don't have a k component for the acceleration. Now, remember, for any of the formulas that we're going to use, well, not any of them, but like for this one, since we already had to calculate the tangential acceleration, I would use the one that requires us to find that, because the only other thing I need in addition to my tangential acceleration is the magnitude of acceleration, which for this is going to be pretty easy. So if I find my magnitude, take the square root. If I square the I component, we get positive b squared cosine squared t. And if I square my j component, I get b squared sine squared t. And guess what, y'all? We can factor b squared out. And guess what, y'all? Sine squared t plus cosine squared t is 1, which means that b on its own is the magnitude of the acceleration vector. Now, if I were to go for my normal component of the acceleration, a sub n, we have the square root of the magnitude of my acceleration squared minus the tangential acceleration squared. That gives us the square root of b squared. Guess what? That's b. And if you think about it, if the tangential acceleration is 0, that means that all of the acceleration is occurring in the normal direction. So in this case, the magnitude of the acceleration is equivalent to the normal component because there is no tangential acceleration. Pretty cool stuff. Which is one reason why helices are so cool. All right, last example. Position vector for a projectile is given by this vector r. We want to find the tangential components of acceleration for 3 different values of t. All right, so here we're only concerned with the tangential component. We don't necessarily want the normal component. So that kind of changes what we might do. Now, starting off, I can find my velocity vector. Same way, just component-wise, taking the derivatives of all of these. So derivative of 50 root 2 times t is 50 root 2. Notice that t is not inside the square root. So it's just a number times t, which is why why the derivative is just the number. All right, plus, and then we take the derivative of this guy. So we get 50 square root 2, and then the derivative of minus 16t squared is minus 32t. Remember, your parentheses are important because there's more than one term in this component. So now I have my velocity vector. Remember, I cannot plug in values of t until after I've gotten my tangential acceleration. Okay, meaning, yes, I am going to take the magnitude of the velocity, but no, I cannot plug any of these values of t in yet. Otherwise, that would just give me the speed of the projectile at various times. That's not what the question asked for. It asked for the tangential acceleration. So we know that tangential component of acceleration is the derivative with respect to t of the magnitude of the velocity. So magnitude of my velocity, I have not taken a derivative yet, so I'm still writing d dt. Magnitude of my velocity is going to be the square root of this guy squared. Side note, 50 squared. 5 times 5, it's 25. There's a 0 in 50 and a 0 in the other 50. So 50 squared is actually 2500. Square root of 2 squared, yep, that's right, it's 2. So if I multiply 2500 times 2, I get 5000. Now for this one, right, we would have to distribute to get that to be what we want. I don't really feel like doing that. So we're just going to do a chain rule with the chain rule inside. And you are more than welcome to distribute if you can do all that multiplication in your brain space. But yeah. So before I take the derivative, I'm going to write this in a way that is convenient for differentiation. So remember earlier we said that that means writing roots as powers. So this is all to the 1/2. Now I can do my chain rule. So I bring my 1/2 down. I don't change the inside. I take one away from the power. And then I multiply by the derivative of the inside. So derivative of 5000, that's 0. I don't need to worry about it. Derivative of this guy requires a chain rule. So for this chain rule, I bring my 2 down. Take one away from the power. And then multiply by the derivative of this, which would just be negative 32. Other thing to note, remember, this is raised to a power. You can't do anything with it. But I can multiply the 1/2 by this, and essentially it's just going to knock out that 2. So we end up with yep. So we end up with negative 32 times 50 square root 2 minus 32t all over the square root of 5000 plus 50 root 2 minus 32t squared. Okay, now this gives me my tangential acceleration for any value of t. At this point, it's okay for me to just plug in different values of t. So to start with, my tangential acceleration when t is 0, this term will go away. We just end up with, we just end up with negative 32 times 50 square root 2, right? That term is 0, divided by, and then that's going to be 0. Remember when we squared this, we got 5,000. So if I add that to the 5,000 that's already there, we get the square root of 10,000, which is equal to 100. So if that's 100, then this will reduce to 1 over 2. And 32 divided by 2 gives me 16. So the fully simplified answer would be negative 16 square root 2. And that's the tangential acceleration when t is 0. When t is 1, all right, we end up with negative 32 times 50 square root 2 minus 32 over the square root of 5,000 plus 50 root 2 minus 32 squared. I don't really have any clever math tricks for that one. So you would have to rely on your handy dandy scientific calculator for that one. And then if t were equal to this guy, yeah, if t were equal to this guy, it would actually end up being super, super convenient. So my tangential acceleration when t is equal to 25 root 2 over 16. We would get negative 32 times 50 root 2 minus 32 times all this nonsense divided by the square root of 5,000 plus 50 square root 2 minus 32 times all this nonsense. And then that's squared. All right. So here's what's going to happen. I know that 32 divided by 16 reduces to just 2. Guess what? If I multiply 2 times 25, what do I get? That's right, I get 50. So we end up with 50 square root 2 minus 50 square root 2. You know what that is? That's 0. You know what 0 times anything else is? 0. And you know what 0 divided by any non-zero number is? That's right, 0. So we end up getting the tangential component for our acceleration for all these different values of t. Yeah, I'm not doing anything with that one. So yeah, that's pretty much it. And with that, we are done with section 12.4. Learned all about normal vectors, tangent vectors, and how we can use it to look at centripetal force, as well as anything that requires tangential and normal components. Happy mathing.